This is Geometry, Chapter 5, Section 4, in which we will study indirect proofs. So far, all of the proofs we've done have been direct proofs. You've started from something given and you've worked your way to what you're trying to prove. And we've used two-column, we've used flowcharts, we've used paragraphs, we've done the algebraic kind where we used it to solve equations. We've done all those different techniques. There's another method, though, called the indirect proof. And this idea, sometimes they call it proof by contradiction, because what you do is you assume that what you're trying to prove is false. And then you show that it can't be false. You get work to something that is a contradiction, something that you know isn't true. And then since you know your conclusion cannot be false, then it has to be true. Okay, it's a whole different ballgame. So I'm going to give you a sequence of steps to think through. Your first step is to assume your conclusion is false. Or another way to think about it, assume the opposite thing is true. If we did a theorem that you're very familiar with, that the sum of the angles of a triangle equals 180, and that's what you're trying to prove, you would assume that the sum of the angles of the triangle do not equal 180. And then you would work from there. And you assume the opposite of what you want. Then you use logical reasoning to get from there to something that you know is wrong. Yeah, I know it sounds weird. You're trying to prove something by proving something is wrong. Bizarre, but we can work with it. Okay. What you're looking for is a contradiction of the hypothesis, the given information, or a definition, or a postulate, or a theorem, or a corollary. Something that you know is true, but then our work goes against it. And then finally, once you've gotten your contradiction, then you say that since the assumption was incorrect, the original conclusion has to be true. Okay. Like I said, you're trying to prove that something cannot be false. And if it can't be false, that means it has to be true. Weird, wacky stuff, I know. Fortunately, we don't have to do too many of them. So they're going to start us off with some relatively easy ones. They're going to ask us to state the assumption necessary to start a proof. We're not actually proving anything yet. We're just saying what the assumption would be. So if they gave me a statement, angle 3 is an obtuse angle, I want to assume something that's the opposite. So I would say, assume angle 3 is not an obtuse angle. Notice here I did not say assume angle 3 is an acute angle, because while yes, an acute angle is not obtuse, I've left out right angles. So I need to cover all my bases. If I just say it's not obtuse, that covers whatever else it might be. Same idea here. If they gave me a statement, x is greater than 5, I need to assume that x is less than or equal to 5. I can't just say assume it's less than 5, because I've left out the possibility of 5. Okay, when you do your opposite, you have to make sure you're covering anything that could be opposite of what you're talking about. Triangle XYZ is an equiangular triangle. Your conclusion would be to assume that it is not equiangular. And you wouldn't just say assume it's obtuse or assume it's acute or assume it's right, because you don't have all your bases covered if you assume just one. You have to cover every possibility. And usually throwing the word not in is the best way to do it. So let's try to write an indirect proof. If negative 3x plus 4 is greater than 16, then we're trying to prove that means x is less than negative 4. Well, if we're trying to prove that it's that x is less than negative 4, we need to assume the opposite. So let's assume x is greater than or equal to negative 4. That's the opposite of being less than negative 4, is to be greater than or equal. So I'm going to pick some value for x that's greater than or equal to negative 4. I picked 1. Okay. 1 is definitely greater than or equal to negative 4. So then, using the substitution property, I can substitute 1 in place of x. So I did that. Negative 3 times 1 plus 4 is greater than 16. That's what our statement would say. When I work it out, negative 3 times 1 plus 4 is the same as negative 3 plus 4, which is 1. So this statement has reduced now to 1 is greater than 16. And last I checked, that wasn't the case. So our statement is clearly false. Well, we've gotten to a false statement. How did we get there? Starting from assuming x was greater than or equal to negative 4. Well, if our assumption is incorrect, then since x greater than or equal to negative 4 is a false thing, the only other possibility is x less than negative 4 has to be true. We assumed something up here, worked with it, found out that it doesn't work, and then we say, well, then this couldn't have been right. So that leaves one other choice. It's basically the idea of eliminating choices. The process of elimination, that's the word I'm looking for. Okay. Let's try another one out. Our statement is if x plus 2 is an even integer, then that means x must be an even integer. Well, we're going to assume the opposite of our conclusion. X is an even integer. What's the opposite of that? Let's assume x is odd. So I'm going to pick an odd number. I picked 3. No special reason, just whatever button my finger was close to. So I picked x equals 3. That's definitely odd. Then plugging that in, I could have typed again by the substitution property, but x plus 2 would be the same as 3 plus 2, which is 5. And 5 is an odd integer. But we were given that x plus 2 is even. So we've got a problem. We have a contradiction. That means our assumption was wrong. Our assumption was wrong, and we assumed x was odd. Well, since x can't be odd, that only leaves one option. X has to be even. Let's apply this same idea to a geometry one and see where we go from there. So we're given some information. We're given that MO is congruent to ON. And we're also told that MP is not congruent to NP. Okay, that's what that symbol is. With the slash through it means it's not. And we're trying to prove that then angle MOP is not congruent to angle NOP. If I'm trying to prove that something is not congruent, I need to assume the opposite. What's the opposite of being not congruent? Being congruent. So I'm going to assume those two angles are in fact congruent. Okay. Well, since they're congruent, that's got me thinking about congruent triangles. And I see my reflexive line, OP is congruent to OP, because of reflexive. Now I've got a side, an angle, and a side, and the angle is in between. Using what we were given, that tells me I've got congruent triangles by side, angle, side. Okay. Now, since those are congruent triangles, that means parts match. And that would tell me that MP has to be equal to NP. Now, the quicker among you see the problem already. MP is congruent to NP is exactly the opposite of what we were told was true. This right here is what we in the business like to call a dirty lie. We were given that it's not congruent, but we just proved it is congruent. So that's a contradiction, which means our assumption was false. Well, if our assumption was false, then MOP must not be congruent to NOP. Okay. Thought so. So that's indirect proofs. Again, yes, I know it's weird, it's tricky, it's funky, but we can get through this. And fortunately, we don't have to do very many of them. Okay. And as always, if you had questions along the way, hopefully you wrote those down. Bring them in and ask questions, and we will see you in class.